moving to now. So magnets cause a space to be modified in the vicinity, forming a magnetic field. And the poles of a magnet are kind of analogous to electric poles or charges, but magnetic fields are separate from electric fields. They're two different kinds of fields. And the North Pole is where the field leaves, the South Pole is where they enter. And one of the key things with magnetic fields is that they are a continuous loop. There's no beginning and end. Whereas you have an electric field, let's say I have a positive charge and negative charge, you know, the field starts here and then it ends here, and then it starts here and it ends here, and starts here and ends here. It's not true with a magnet. Magnet is a continuous loop. And so if you've ever done the iron filing lab, this is kind of fun. You know, you sprinkle iron filings on top of glass, and they separate out. And so in our lab, you were able to draw this out, you know, using the compasses and drawing. And so it's helpful to be able to see that. Let's say this is our North Pole, this is our South Pole. We have our field that passes through the middle, coming out of the North Pole and then down into the South Pole. And if you notice here, it's a continuous loop, right? It goes up and around and then through. And that's what we have with magnetic fields. So, you know, we've got our field passing right through the middle of the magnet, up out of the north into the South Pole. One of the really interesting things about this is, you know, in the Earth's core, we have our molten core that's, you know, moving around, and we have our magnetic field, and our magnetic field's actually essential for life. If we didn't have our magnetic field surrounding us, the Earth's radiation would, you know, destroy life on Earth. And so this is a critical part of our life on Earth, having the magnetic fields. So our compass seeks, if you notice, you know, in that lab, the compass itself actually points to the South Pole. So what's a little bit weird is the fact that if you look in the Earth, the northern part of the Earth actually is the southern part of a magnet, of the magnetic field, and then the bottom part of the Earth is north. And so when you have your compass, the compass is actually pointing towards the south side of Earth's magnet, which we call the North Pole. So that's a little counterintuitive there. And so compasses, you know, are themselves magnets, and they're easy to rotate. Some are in fluids, some are just in air. The ones we used in class are just suspended in air. If you look at the picture of the aircraft in the back of our room, that compass in there is filled with white propane. Yeah, as you know, it's just floating around. And so the compass points towards Earth's north magnetic pole. But again, what's crazy is that it is the south side of Earth's magnet. And so even though we call it the North Pole, it's the south side of the Earth's core magnet. Okay, so one of the key things that we want to talk about as well is that there's no such thing as a monopole, because a magnet itself, when you split a magnet, because that field, you know, continues on through, you know, you can break it up and then you can have a North Pole and a South Pole. You know, in this case here, we've got, you know, a large magnet. If we split that in half, what happens is this portion is now just considered north, and this portion is considered south. We could keep splitting them really all until microscopic size, and you're going to have a north side and a south side. That's because, you know, there's certain objects that are called ferromagnetic that can be made into strong magnets and can stay in that form. And so when a material is unmagnetized, the domains are randomly oriented. But if you can get them to line up and you get the spin of the electrons, you know, we've got our nucleus here, and then we have our electrons, and those electrons are spinning one way or the other, and the spin can be changed. And if you can get the spin all to line up with a bunch of sets of atoms, you can get a you know, a permanent magnet. Now, if you take that magnet and you start, you know, hitting it against the floor or just dropping it, or just over time, those domains are going to start to switch and flip and become unmagnetized eventually. But you can remagnetize it. You can set it up. We have a device in our classroom actually that'll do that, and reset those the spin so that the magnetic fields are set up in the same direction. Magnetic force on particles is a really important thing, especially in the Large Hadron Collider, where you're taking protons close to the speed of light and smashing them together. The magnetic fields are responsible for keeping it in a loop. The electric fields speed up the particles, but then the magnetic field keeps it in a loop. And so, magnetic force is exerted on a particle. If it meets these requirements, the particle itself has a charge. The charge is moving at least a portion of it perpendicular to the magnetic field. If you have a charge that's moving in the same direction as a magnetic field, there's not going to be any force on it. And this is the first right-hand rule that we're going to use. And so the best thing to do, and it's tough if you miss this lesson if you were gone, but you can do this at home. Just be disciplined to do this well. Set up or hold your right hand out and make sure it's your right hand, not your left hand. Especially if you're left-handed, you may forget, so be careful. Your thumb represents the force on a charged particle. Your pointer finger represents the velocity of a charged particle, and your middle finger represents the direction of the magnetic field that's being encountered. Now, these all three have to be at 90-degree angles. The force is at a 90-degree angle to the velocity. The direction of the magnetic field is perpendicular to the velocity, and we can figure out the force on a charged object. So, and then to remember this, it's FVB, F force, velocity, B for field. So we have a proton going north, experiences a magnetic field going east to west. We want to figure out which way it's forced. So here's our proton going north. The field is going from east to west. And so what you're going to do, and I'd suggest going ahead and drawing this out first on your sheet of paper, but then use your computer screen and orient your hand based on your computer screen here. And then, this will be good practice, and I'll have you use your sheet of paper as well, but let's do the computer screen. So what I want you to do is hold up your right hand, and what you're going to do is you're going to have your pointer finger, if let's say you're looking at a computer screen, you're going to point at your ceiling. So your pointer finger is going at the ceiling. Now your middle finger should be pointing to the left, so from right to left. So as you're looking at your screen, your middle finger should be going right to left in front of you, and then your thumb should be pointing at your face. So what would happen is this particle is going north and experiences this field, and it would fly out of the page, and that's what the particle will do. Now, I show this in class. I have a rocket, a little model rocket, and I show it to everyone. And when the rocket is pointing at your face, you see a dot, and so a dot represents, or a dot and a circle represent out of the page. This is the first time we've really had to use the third dimension, and it's really helpful here. So let's say we have a proton in this one that's going into the page and experiences magnetic field going from north to south. So let's go ahead and draw this. We have the field that is going, like this, and then the particles going into the page. And I showed the other side of the rocket. The other side of the rocket has the tail. It's got an X, so X means into page. So let's go ahead and try this one. We'll do this together. So get your right hand set up to where your pointer finger, thumb, and middle finger are all at 90 degrees. And what you're going to do is you're going to point into your computer screen. So point into your computer screen, because the proton is actually going into your computer screen. And then take your middle finger. Your middle finger should be going towards the floor. So your pointer finger is going into the screen. Your middle finger should be going towards the floor. And which way is your thumb pointing? Well, if you got this right, your thumb should be pointing to the left. So if this particle was going into the computer screen, and the computer screen, you had a field that's going, towards the floor, the particle is going to be forced to the left. Now, what I'm going to have you do is use your sheet of paper now and orient your hand on your sheet of paper. Now the trick is, this is what you're going to do on your test. You're going to want to set up your picture on your sheet of paper itself, and then you're going to orient your hand on your sheet of paper. The trick here is not to look at the screen. So you know, if we can, you know, I can't block the screen right now, but I kind of want to. But what you're going to want to do is look at your sheet of paper and orient your hand on your sheet of paper. So what you're going to do is you're going to point into your sheet of paper. Your middle finger should be going from you know, towards your belly button. So pointing into the paper, your middle finger towards yourself, and then your thumb should be going to the left, just like we did with the screen.